I'm John Dersch. I'm going to talk today about, I'm going to talk about two problems that I encountered when I taught pre-calc. Actually, first ran into these a few years ago. This is what's on the orange sheet, okay? So I don't know how easy that is to read, but the orange sheet, you've got that in front of you. These are two problems from section in our former Precalculus text. I actually brought it. It's the Hungerford-Shaw text. This one right here, from the section on logarithms. And I saw these problems, and I saw this number, and I was convinced that there was something up. And I found out what it was, and I thought, you know, there's a talk here. So that's what I'm doing. And when people will talk to me about giving math seminars, they say, well, what do I give it on? And that's easy. You give it on something that you find really interesting. That's what this is about. This is an excuse for me to talk about stuff that I think is cool. Okay? And I hope you think it's kind of cool too. We're going to start by going through this problem essentially one line at a time. And that means we're going to start with 88A. And 88A, a harmonic sum. Well, we can stop right there. There's going to be a lot of interruptions in this talk. We can stop right there. Harmonic sum. Why the word harmonic? When you, probably everyone in here knows more about music than I do. Okay, I know very little. But if you pluck a guitar string, it'll vibrate over its entire length. That gives you the fundamental, but it'll also vibrate over half of its length, and a third of its length, and a fourth of its length, and of course, you see the full length and a half, and a third and a fourth. It's called the harmonic series because you're basically adding up the harmonics that make up the tone when you have a musical instrument. And I've told you everything I know about music. We need someone to give a talk someday on the relationship between mathematics and music. And it's not me. I think I got the math background, but the music background I do not have. So I'm just going to throw that out. I will throw out several suggestions for talks as I go through this. But right now, we need to do 88A, compute those three sums. Well, this is exactly as simple as it appears to be. You simply add those up. So for the record, just so we can keep track of things, the enterprising student doing 88A gets 25 twelfths, 137 sixtieths, and 49 twentieths. Okay. Now, B, how many terms do we need in a harmonic sum for it to exceed 3? This is already exactly 2.45, so we're pretty close. And so the author's intention was just keep adding. Your calculator, keep adding terms. And it turns out that the answer to 88B, easily obtained with a calculator, occurs if you use 11 terms. 11 terms produce a sum of approximately 3.02. So that's just like warm up. Things get a little more interesting when you get to 88C. It turns out to be hard to determine how many terms you would need for the sum to exceed 10. It will take thousands of terms. Now remember, this is a pre-calc book, okay? So there is no intention here that the student who reads this has seen calculus and has any idea what we mean by a convergent or divergent series. And I don't really know how a typical pre-calc student would interpret this, but if you think about what you're doing, you're adding up 1 plus a half plus a third plus a fourth, and you know you're going on, well, forever. The terms are getting smaller. And if the terms are getting smaller, there's a possibility that it won't just keep getting bigger and bigger and bigger. And what I'm getting at is, what right do we have to even assume that this sum will exceed 10? Because there are sums not too different from this that will not exceed 10. You may be familiar with this one. And maybe you've never seen it before. It's called a geometric series. It's got a common ratio 1/2. First term is 1/2. And depending on how much you've studied, you might know a variety of ways of summing this. And when I say summing this, actually adding up all of the terms. Well, my purpose right now is to not discuss what the exact sum is. My purpose right now is to address the issue, is this even finite? Because if you can add up thousands of terms and eventually exceed 10, that makes you wonder, could you exceed 100 or 1,000 or 1,000,000? Is it possible to have a sum like this grow forever? Or must this eventually reach some fixed value? What about this? Will this grow forever, in which case we would say the sum is infinite? Or does it eventually reach a point where it stops or approaches a limiting value, in which case we'd say the sum is finite? Well, it's easy to show that this sum is finite. Okay? And you may have seen this argument before. It's too cool to not do, it only takes like 2 minutes. Draw a square. With side 1. Okay? So, tough question, what's the area of the square? 1 square unit, yeah. All right, so the area of that square is 1. So now, equally tough question, if I cut that square in half, then this area here would have to be 1/2 times 1. This area is 1/2. If I cut this side in half, then this area is 1/4. If I cut this side in half, this is 1/8. And if I keep doing this, I get 1/16, and I get 1/32, and I get 1/64. And basically, if I keep going, is it possible for this sum to exceed 1? It can't happen because you're adding up the areas and they all show up inside of a square of area 1. It is impossible for this to be greater than 1. So this is finite. Now, some of you may even have a sense of what the sum is. What do you think it is from what you remember in previous work? It's 1. Now, I'm not going to write that. I'm not going to write equals 1 because there's a little bit of discussion that's been going on for years about that. Dr. Niles is in the audience here from chemistry. I think, Tom, that you and I someday have to give a dual talk where we talk about stuff like this, because one of us feels that the answer to this is exactly 1, and one of us does not. Is that a fair summation? Okay. All right. We need to talk about that. Maybe next academic year. And if it's going to be a debate, we can have... if it's 2 chemists against 1 mathematician, I got no problem with that. Okay? We'll have to do that maybe next academic year. So. Now, this one. So apparently the author is convinced that if we add up enough terms, we'll get something that exceeds 10. Well, so just how big will this sum get if it will exceed 10? It is not difficult to show that, in fact, this sum will exceed any positive number. And again, it depends on what courses you've taken. You may have seen this argument before. I'm going to go through some, I guess what you say are plausibility arguments in here. There aren't going to be any formal proofs in here today, but there'll be enough to at least give you some sense of what we're talking about. I'm going to start with this. These 2 terms right here, 1 plus 1/2, that is certainly bigger than 1/2. 1/3 plus 1/4, well, 1/3 is bigger than 1/4, so 1/3 plus 1/4 is bigger than 2/4, which means that's bigger than 1/2. If I add these 4, I'm adding 4 fractions. Every single one of those fractions is at least as big as 1/2. These are all bigger than 1/2, so if I have 4 fractions, and they're all at least as big as 1/2, then that has to exceed 1/2. Now, the beauty of this argument is you can just keep doing it. I would need 8 fractions here. So let's say, I guess we go up to 1/15 then. I now have 8 fractions here. Oh, wait a minute. I need one more. I need to go out to here. Sorry. 8 fractions here. Each one of them is at least as big as 1/16. You add those up, you've got something bigger than 1/2. You can do that again, and you can do that again, and you can do that for as long as you'd like. So whatever this is, it exceeds 1/2 plus 1/2 plus 1/2 plus 1/2 forever, and so the sum is not finite. And it's typical in a situation like this to abbreviate that by saying that the sum is infinite. Okay. So this sum will exceed 10. It will exceed 10. The question then is, who first figured this out? Who was the first person to actually establish that this series, which has a chance of converging, I mean, the nth term goes to 0. That doesn't guarantee anything, but at least it has a chance. Who was the first person to show that this series actually grew without bound? And that was Nicole Orem. 1323 to 1382. He basically established this result around 1350. The exact date is not known. He's an amazing gentleman. Aside from showing this around 1350, he also was the first, as far as we know, to use not only rational exponents, but also irrational exponents. He actually considered things not with this notation, like this, centuries before anybody else did. He did it to refute astrology. That's an interesting argument. It's way too complicated to get into today, but he essentially said astrology is bunk, and here's why. Okay? There was no astronomy in the 14th century. It was all astrology. He questioned Aristotle's teachings. In 14th century Europe, the Catholic Church reigned supreme, and Aristotle was second. If Aristotle said something was true, it was true. Aristotle was wrong about quite a few things, but he did lay the foundation for what was essentially the mainstream of Western civilization, the thought behind it for a couple thousand years. Aristotelian thought was the foundation for what we now take for granted in many areas. And Orem questioned a lot of what Aristotle did. Aristotle was convinced that the Earth did not rotate, and Orem proposed that it did. And that was 200 years before the Copernican theory was put forth. He was also a budding physicist, and this is at a time when there really was no physics. Physics as a discipline did not really come into its own until the late 1500s, early 1600s with people like Galileo, and then after that, of course, Newton. Gave a geometric demonstration of the mean speed theorem. This is the mean speed theorem. In our minds, this seems almost trivial. It's like, okay, an object moves with constant acceleration. You got an initial speed, you got a final speed, you got an elapsed time, you've got a distance traveled. How do you find the distance traveled? Well, you know, you take the beginning speed, take the ending speed, you divide by 2, you find the average speed over the time. Distance equals rate times time. You're done. You have to appreciate how advanced this thinking was at this time. Nobody had ever considered quantifying change until Orem and some other people associated with Oxford University in England around the same time period. They just didn't. You didn't quantify it. I mean, it was clear that, oh, look, it falls, and it starts out going slow, it ends up going faster. I mean, that's obvious, okay? But to try to actually come up with some formulas to describe what was going on in the situation, this was cutting edge stuff. in the 1350s. What Orem actually did that was a step beyond just thinking like this is he gave I'll call it a geometric demonstration. Some people would call it a graphic, as in graphing things like we do in an XY coordinate system. Some people would call it a graphical demonstration. I'll stop short of that. He gave a geometric demonstration of this, okay? So, and if you've had a little bit of physics, you're familiar with velocity time graphs, this is going to look familiar. He drew a horizontal line. The length of that horizontal line was t. Okay? Then he reasoned that, okay, an object moves with constant acceleration, so as time passes, it's going to go fast, and then it's going to go a little faster, and it's going to go a little faster, and the rate at which its speed is increasing is constant, because that's what constant acceleration is. So what he did is he drew this picture. It's like, okay, I'm going to let this represent the initial speed. That's v naught. Okay. And then as time goes on, it's going to move a little faster. So I'm going to make that a little longer. And then as time goes on, it goes a little faster. I'm going to make that a little longer. And he just basically kept doing that. And there's no specific numbers here. He didn't make this exactly 1.5 times bigger than that 1.5. He just basically said, you know, they're going to get these, he called them intensities, are going to grow at a constant rate. And then this is your final velocity. And then he said, well, you know what? All we have to do is find that area. And that area will be the distance. Because that's a trapezoid. There are two ways to do this. It's a trapezoid, right? How do you find the area of a trapezoid? Add up the parallel sides, take their average, multiply by the height. That's this. Or, if you take the average of these two, you're basically going up to here. You're going across. This is supposed to be the same size as that. If this is the same size as that, then this average speed takes place over the entire interval. Distance is rate times time, and you've got the same answer. He gave a graphical geometric demonstration of this. This is more than 250 years before there was anything that we would call a coordinate system. And there is some speculation that Descartes, you know, the Cartesian coordinate system, that Descartes and Fermat, who also developed coordinate systems in the 1630s, were influenced by Orem. Orem is French. Descartes, Fermat, they're French. Orem was well enough known, so his works were kept in libraries. It's possible that the two of them actually saw this work and were influenced by it. We don't know that for sure. One thing we do know for sure is that Galileo saw this and this in Orem's work. In fact, in the early work that Galileo published on motion of falling objects, not only does that formula appear, but it appears with a drawing that looks basically just like this. So Orem foreshadowed the work of Galileo by about 250 years. He was way, way, way ahead of his time. And he did all of this without stuff we take for granted. Okay? You see this right here? There's exactly one piece of this that existed in Orem's time. The fraction bar. There was no equal sign. There was no plus sign. Didn't use variables to represent things because what do you mean? Letters are letters, numbers are numbers. You know, the variable, there was no such thing. Okay? This was all written out in words. But if you wanted to write a fraction, you did have a fraction bar. Not only did he do all of this 250 years before Galileo, and close to 300 years before Descartes and Fermat, he did it in the mid-1300s. I don't know how good or how much you know about European history in the 1350s. That was a bad time. That was a really bad time. It is arguably one of the most catastrophic periods in the history of humans inhabiting this planet. It was the Black Death in Europe, the plague, the plague. Population of Paris went from 100,000 to 50,000 in 3 years. or M was studying in Paris at the time. Now, not much is known about his personal life, okay, but it would be difficult to not pay attention to the fact that every day bodies are being carried down the street and people are dying, and he's still finding time to do this. It's amazing. At a time in what might be considered one of the lower ebbs in European history, you had one of the brightest lights shining here in terms of what was going to come in the future. This is the foreshadowing of a lot of very important ideas in physics. So he was a very remarkable gentleman, and he was the one who established that this is the case, which I think brings us back to the problem we're supposed to be doing. Let's see. Where are we now on this anyway? I think we probably, we still haven't done 88C, have we? We should probably try to do 88C now. There. So it turns out to be hard to determine how many terms you would need for the sum to exceed 10. Using calculus, we can derive this lower bound formula. And it's true. In Calc 2, although you could actually do it in Calc 1, you can derive the formula that's given, the lower bound formula, that this sum I running from 1 to n of 1 over I is, well, it's a lower bound formula. So that sum must be greater than the natural log of n. If you're not real familiar with this notation, that's just a shorthand way of writing 1 plus 1/2 plus 1/3 plus 1/4 plus 1 over n. Basically, this formula tells you that if you're going to add this up, it's got to be bigger than the natural log of the number of terms. Okay. Well, if we want the sum to exceed 10, if we want this to be bigger than 10, it'll suffice if we can make this bigger than 10. So, natural log has to be bigger than 10. Convert to exponential form, and that's why I wore this shirt. N has to be greater than e to the 10. E to the 10 turns out to be approximately 22,026.5. The only reason I remember that is I just saw it a minute ago. And so you could use this many terms. 22,027 terms. Okay? So if you added up 22,027 terms, you'd have a sum exceeding 10. So we have an answer here. Then there's 88D. Calculus gives us an upper bound formula, estimate the harmonic sum with 100,000 terms. So it's supposed to add up 100,000 terms, and if you do that, how close is the estimate to the real number? Now this one interested me for more than one reason, but the first part is what we'll do. Estimate the harmonic sum with 100,000 terms. Okay, so the sum has to be smaller than this, and it has to be bigger than that. So you basically can just set up one of these. The sum that we are interested in, we're going up to 100,000, has to be less than 1 plus the natural log of 100,000, has to be greater than the natural log of 100,000. Well, you grab a calculator and plug in some numbers, and you get this. This is 11.513. This is, of course, 12.513. By the way, if you've not had any calculus, I advertise this talk as something that doesn't need a lot of calculus. We're going to do almost no calculus in here. But if you're wondering, well, where does this actually come from? It's not difficult to establish this result. The upper and lower bound formulas, it's not hard to establish these except for one step. Most of what you do involves comparing areas. You draw appropriately labeled graphs, and you compare area involving a bunch of rectangles to area under a curve. So coming up with the inequality is not difficult. Coming up with the natural log is the part that takes some calculus, because in order to come up with the natural log part, you have to be able to find the area under y equals 1 over x above the x-axis for x equals 1 to x equals any n that you're interested in. You can set that up by summing. This means you're adding things up. Basically, length times width, the height of a rectangle times its width. You sum that up from 1 to n. The calculus part comes in by knowing how to evaluate that. It turns out that you need something called an antiderivative. The antiderivative of 1 over x is natural log x. You evaluate that between 1 and n, and that's where the natural log of n comes from. So the derivation is not all that difficult, but you do need a little calculus knowledge to get this. So the sum is in here. The sum is between basically 11.5, 12.5. But this part intrigued me. How close is your estimate to the real number? I'm thinking about that. I'm going, which real number? It's pre-calc class. You're dealing with real numbers for the most part. And then I realized, oh no, he meant, well, by the way, this is Hungerford Shaw text. Shaw wrote this problem. I know because I contacted him. Okay. Shaw wrote this problem, and I asked him, so what did you have in mind here? He said, well, I had in mind that I would have provided the actual sum, but I forgot to do that. Okay. So see, now that raises the question, how close is your estimate to the real number? What is the actual sum? And this gets interesting. Actual sum of 100,000 of these terms, we have Maple software. And you can ask Maple to find the sum of the first 100,000 terms. Now, look, you got to understand something. In theory, you could do this by hand. It just depends how much time you want to spend. You know, could you add up the first 100,000 numbers, 1 plus a half plus a third? Sure. You know, give me a few weeks, a lot of paper, could do it. So the answer is a fraction. All right. Well, if you ask Maple to compute this sum, there may be a way for it to give you the fraction, but it's kind of a lot of digits, so that wouldn't have made much difference anyway. According to Maple, it's approximately 12.09015. Okay, which is, you know, in between there. In fact, it's not too far from the average of those two, which is kind of nice. But Maple being Maple, it'll also give you the exact answer. It's exactly psi of 100,000 plus gamma. Now, if you've ever used Maple and you get things like that, it can be a little bit discouraging because it's like, I don't know what that means, but there's a help menu, and you poke around with the help menu. That's how you learn things, you know. So I'd actually seen that function before, but I did poke around with Maple. And let's see, where do we need to be? We need to be here. Psi of x is the digamma function. That's not particularly helpful. It's the derivative of the gamma function divided by the gamma function, but that's not helpful either. What's the gamma function? Okay, Euler, and I think it was Mr. Lee who said that it seems like Euler comes up in almost every talk that's given in these seminars, and he may be right. Euler was the first one to essentially be playing around with integrals like this, because, I mean, come on, wouldn't that be fun? Back around 1730, and he proposed that since this is an integral with respect to t, you could define a function of x to be based on what this exponent is. And so he messed around with that. It was actually Legendre, almost, well, I was going to say a century later, not quite, who defined this particular form. Those of you with a calculus background, exercise your homework for tonight. All solutions are due tomorrow at noon. Is to get from here to here by making an appropriate substitution. Okay? That's a Calc 2 problem. You guys can do that. Okay. All grade on a curve. This right here is the more commonly encountered version of the gamma function. And I told you there wouldn't be much calculus. It's going to be just a little bit here, just a little. Gamma function is a very interesting function. Given a talk on just the gamma function, that would be cool. That would be really cool. So what would gamma of 1 be? We won't take the time to evaluate it, but if you've had Calc 2, remember gamma of x, so x is 1, t to the 0 is 1, you're summing 0 to infinity e to the negative t dt. That is a really easy improper integral, and that turns out to be 1. Gamma of 2, well now you have t to the first here, so you have e to the negative t, t to the first dt, and that is also an easy integral because you would use? You would use parts. Excellent. Would you like another apple? And if you evaluate that integral using parts, you would get 1. So gamma of 3. Now you've got t squared. You could use parts twice, or you could use tabular parts. It's really effective here. And that turns out to be 2. Gamma of 4 turns out to be 6. And you ought to be getting some idea that there's a pattern here, especially when you see this one. It turns out that gamma of n, where n is 1, 2, 3, 4, 5, is exactly n minus 1 factorial. The gamma function is known as the generalized factorial function. And the generalized factorial function basically says, you know what gamma of x is? It can be interpreted, depending on how one wishes to interpret notation, as this. For any real x, except 0, negative 1, negative 2, and so on. In fact, it can be defined for any complex x as well. It just gets more interesting when you get into the complex arena. This allows one to come up with some interesting things that I will occasionally bring up in class just to, I don't know why sometimes. My students might give you some suggestions, but don't ask them. So for example, gamma of 3 halves would be 3 halves minus 1. 3 halves minus 1, it would be 1/2 factorial. And 1/2 factorial turns out to be square root of pi over 2. And there are ways, there's some relatively straightforward ways of deriving that. This is, in my mind, this is really cool. I carved this on a pumpkin one year for Halloween. I always carve math on my pumpkins for Halloween. I'm thinking of a variety of things of responding to that. One of the pumpkins that I carved one year was this. Was on there.
When are you going to explain that one?
Someday. And underneath it, you said scary, so it made me think of this. That's another talk. Anyway, so you run into some really interesting stuff when you just poke around a little bit with a problem like a precalc problem. Now then there's this, the gamma. Okay, I erased it, but it was, what did I say, psi of 100,000 plus gamma. Gamma is Euler's constant. Gamma is basically the limit of what happens when you take the area between a bunch of rectangles and a curve, or an area under that curve. And Euler was the first one to realize that when you add up all of these and you subtract this and you let the number of terms n grow without bound, you get a limiting value. This is a very, very interesting number. Not much is known about it. It's not even known if it's rational. I don't know if any of you saw a movie. I did not see this movie. It breaks my heart that I didn't see it. Movie came out in May. Maybe it was late April, early May. The Man Who Knew Infinity. You saw that? Anyone else see that? Did you see that? Was it good?
Oh, yeah.
Okay, it's based on a book that came out in '91. Same title. It's about Srinivasa Ramanujan, and a genius, maybe one of the greatest mathematical geniuses of all time. And his mentor in England was G.H. Hardy. And G.H. Hardy, who was played by Jeremy Irons in the movie, G.H. Hardy had an endowed chair at Oxford. He was one of the greatest analysts of the first half of the 20th century. And he said, anyone who can prove that this is either rational or irrational, I will give you my endowed chair in mathematics. He would give it up for anyone that could do that. And no one's ever done it. So not much is known about that number. There's another talk there. All right, well, let's see. We still haven't gotten to problem 89 yet, have we? I guess we better get going here. Oh, no, not yet. We have some other things to talk about first. The title of the talk, I forgot the title of the talk, it's Some Sums. One of the reasons I decided on that title was when you talk about the harmonic series, you have, of course, this. This diverges. It sums to infinity. So I won't write on the screen, although I'm tempted. This equals infinity, okay, in the sense that it grows without bound. So what if you got rid of some terms in the harmonic series? What if you got rid of half of them? So basically, I got rid of all the terms that had odd-numbered denominators, and so I'm left with this. We have half as many terms, but it's like, well, yeah, but isn't that just half of infinity in some loose sense? And it really is not bad to say that, because if you took this and you multiplied it by half, you would get that. And if this sums to something that grows without bound, then so will that. The interesting thing is there's really no limit to what you can do with that. If I multiply this by a half, I get that. If I multiply this by 1/1,000,000th, I get this. And that'll still diverge. Even though these terms, in terms of their denominators, are a million apart, it's like, yeah, it's still going to diverge. Okay? All right, so let's look at something a little different. What about this? This is the sum of the reciprocals of the prime numbers. Does the sum of the reciprocals of the primes, does that diverge? It might if there are infinitely many primes. That's one of the oldest results known in number theory, that there are, in fact, infinitely many primes. Euclid proved that in his famous book, The Elements. It's an elegant proof. It's very nice, that there are infinitely many primes. But that does not necessarily mean that this converges or diverges. If, on the other hand, we knew for a fact that there were only a finite number of primes, then talking about that diverging doesn't make any sense, right? Because if there's a finite number, you add them up and you're done. Well, this does diverge. This series diverges. The proof of that, I contemplated preparing a proof of that for this seminar and realized that it would take way longer than we had. It's a fairly involved argument. There's several proofs that I'm aware of. I talked to Radu Teodorescu, one of our adjunct, and asked him about this, and about a week later he said, I have a proof for you. And I think it might have been when he came up on his own. I haven't talked to him yet, so I have to talk to him about that, see what he's got. This diverges, okay? So if you look at the sum of the reciprocals of the prime numbers, you get infinity, which establishes indirectly that there must be infinitely many primes. Because if the series diverges, the only way it can diverge is if you have infinitely many things to add up. Okay. Well, the next logical direction would be to look at twin primes. Twin primes are primes that are separated by exactly two numbers. So the typical way of ordering them is 3, 5, 5, 7, 5 is repeated here, 11, 13. Our department head came by and wanted to know if I'd made a mistake in my flyer because I had 2 fractions of 1/5. And I'm glad he did that because I make mistakes all the time. But in this case, it's okay because you do this because there's that. You do that because it's there. You do that because it's there. Our department head is fond of trying to give me a hard time because that's what I always do to him. Does that converge? Now, this is an intriguing question because if the answer to this is no, if it diverges, then we would know something about twin primes. There's a very famous problem out there. It's called the twin prime conjecture. And the twin prime conjecture is there are infinitely many of these pairs. That's the conjecture. Now, conjecture is something that is thought to be true but has not been proven. Well, to this day, no one knows if there are infinitely many twin primes. If this series diverged, we would have an answer. It can't diverge unless there's infinitely many, so the answer to the question is yes, and it was Viggo Brun, Norwegian, who proved this in 1919. And this is the sum, approximately, and again, no one knows the exact value. But I had to mention this as well because I lived through this. Some of you did. Some of you don't, maybe have no idea what I'm talking about. In 1994, there was a bug found in one of the new processing chips that came out from Intel. It was their Pentium chip. It was the next generation of processing tools. And it was great until it was found that it had a bug. It did not know how to divide correctly. Intel put out a chip that would not divide large numbers correctly. And Thomas Nicely is a mathematician who was actually working on the problem of approximating this sum. And in order to do that, he was working with 14-digit twin primes, which basically meant he had to take 1 divided by 14-digit number. Well, the Pentium processor that he was using didn't work. It gave errors. He became famous. I wasn't on the cover of Time magazine, but he was in it. He was quoted as saying that ordinarily a mathematician would have to shoot someone to get this much attention. He was actually working on twin primes when that bug was found. So that particular sub-series converges, and then you've got this. Kempner series. Aubrey J. Kempner, he was a mathematician. Born in England, educated in Germany, came to the United States just before World War I, and right about that time was messing around with sub-series of the harmonic series that are dealt with like this. Start with your harmonic series, delete all terms whose denominator contains a given digit. So, there you go, but wait a minute. I'm going to delete the digit 2. So I'd have 1 plus, I got to get rid of 1/2. Then you got a 3rd, a 4th, 5th, 6th, so on. 10th, 11th. 12th, nope, that's gone. 13th, 14th, 15th, 19th, yeah. 20th, nope. In fact, nothing, 20, 21, 22 in the denominators, those are all gone. Once you get to the 30s, you got to get rid of 32, 42, 52. When you get to the hundreds, you get rid of a few, but when you get to the 200s, they're all gone, right? Okay, so start with a harmonic series, delete all terms whose denominator contains a given digit, such as 2. Well, he was able to prove that since nearly all integers contain the digit 2, we end up deleting nearly all the terms, and so the series converges. That's something you want to think about a little bit. If you're thinking, what do you mean? Almost all integers contain the digit 2. I can give you lots of examples of integers that don't contain 2. 37, 38, 39, 40. Start thinking about how many integers there are. Positive integers, of course. You know, how far are you going to go? There's no limit. Start thinking about 100-digit integers, 1,000-digit integers. How likely is it that if you picked a 1,000-digit integer at random that it would contain no 2's? Since almost all integers contain 2, we end up deleting almost all the terms. This series converges. It's interesting stuff. Now I think it's time to get back to finishing these two problems because we'll run out of time if I don't get to it. So where are we at? We did 88, 89, 89. Ancient Sumerians, Babylonia, Mesopotamia, that area. Present day Iraq, Iran, in that area. Started using a place value system around 3000 BC. So assume that in 3000 BC you started adding those terms at a rate of 10 additions per second. Faster than a human would do it, slower than a computer would do it. I'm not quite sure why 10 was picked, but we'll go with it. Okay? What would the value be today? Make your best guess. I'll let you do that on your own. 89b. Use the upper and lower bound formulas given in the exercise to estimate what the value would be today. Was your guess close? Okay. The upper and lower bound formulas from 88. Are these. The sum, I running from 1 to n, of 1 over I, is less than 1 plus the natural log of n, is greater than natural log of n. Well, we've got to find out what this gives us. We have to know n. So n, let's see. We'll assume that 2016 is come and gone, so that's 5,016 years, right? And then we just do some conversions. 5,016 years, 365 days in a year, 24 hours in a day, 3,600 seconds in an hour, 10 computations per second. It turns out that you'd have to do this many computations. So n is approximately 1.582 times 10 to the 12th. Okay? And that gives you 28.09 less than the sum, less than 29.09. Now, I don't know how well I don't know how well you guessed this, but according to our upper and lower bound formulas, this is the answer to 89b. Well, now we get to the part that had gotten my attention from the very beginning. In what year are you guaranteed to be above 28.187? Well, that doesn't look too far off. You want to be above 28.187. You want n such that remember, this is your lower bound formula. You want the sum to be above 28.187. So you want that lower bound expression, natural log n, to be more than 28.187. So, natural log n. And so n must be greater than e to the 28.187. And you compute that, and you get n is approximately 1.74365 times 10 to the 12th. So you'd have to add up that many terms. Well, no, that's not true. That's how many computations you would have to do. The author asked what year, right? So what do we have to do now? Got to go backwards, convert that to years. So you divide by 10. You divide by 3,600 seconds in an hour. You divide by 24 hours. You divide by 365 days. And if you do that, so this is a number of computations. This is how many computations you're going to do. And that turns out to be, rounded, 5,529. Now that's not the year, right? That's the number of years. So this would take place in what year? Take 3,000 away from it, right? So in the year 2529. Now that's the answer in the back of the book. It's an odd numbered problem. I'm no fool. I checked the answers in the back, okay? That's the answer in the back. I saw that answer and I said, nope, that's not right. It's not right. I knew it wasn't right. My gut told me that's not right. Then I thought, well, I must have screwed up somewhere, but I couldn't find a mistake, but it didn't take me long to realize that the mistake that I hadn't made a mistake. The mistake that they had made was how many days in a year? 365 and a quarter. If you're going over long periods of time, whoever wrote up the solutions manual forgot about leap years. So I went back, redid the problem, and I used 365 and a quarter, and I got this.
In the year 2525, if man is still alive.
I won't make you listen to all of this. I actually debated whether I was going to do it, but you know, it's so cheesy. You know, look at that futuristic setting. Isn't that just really far out? This, if you're not familiar, if you're of a certain age, you remember when this song came out. That was 1969 that song came out. It was a number one hit nationally for several weeks. And I figured I'd show it because it just has that great late 60s look to it. It really does. I was 14 when that song came out, and I really liked it. It was really cool. Okay. So I knew when I saw this problem originally, I saw the 28.187, I figured this had to be the reason, is that it was going to be in the year 2525. And so that's what got me started. And that's basically all I've got. So thanks for coming. I don't know if you have any questions about anything. We went in a variety of directions here, so I guess it's up to you if you have anything you want to ask me now or later. Is there any questions right now? Yes, sir.
Yes, I'm kind of curious about the number 23.187 also.
Yeah.
Why do you think they chose that particular number? Did they have that?
Oh, Shaw of Hungerford and Shaw, his exact wording was, and this is email, I didn't go visit him, he's at the University of Iowa. I didn't stop there this past summer, but he said, this makes me a little sad actually, and I'm not sure if it's sad about me as a person or sad about other people. I'll let you decide. I instantly thought this is the reason. So I asked him, and he said, yeah, this was the reason. This is Hungerford and Shaw were the authors. Hungerford has since passed away. But Shaw, he said, no, this is my problem. I did it as a joke, and you're me, the first person to have gotten it. And I thought, how sad is that? And then I thought, well, wait, yeah, how sad is that, reflecting on me or on everyone else who should have assigned this problem and realized this is really cool. But that's why. The only reason that 28.187 is there is so you end up with the year 2525. And E gets pretty big if you make it 28.188. It's a little bit too much. You go too far out. So yeah, that's the reason. That is exactly the reason. It was a joke.
Revisionist, because if that's the answer in the back of the book, 25.29 you said was in the back of the book, though. Maybe you gave him the idea.
Oh, I know. I didn't correct him on it. I actually contacted him fairly well. I contacted him when I realized I was actually going to be giving this talk, and I was always curious as to where exactly. Oh, I don't like that song. I was always curious as to, to me, this was not a coincidence. It was not. I just was curious if there was a backstory, and there was a backstory. It was a joke, and really no one got it except you. Any other questions?
Sounds like some of my jokes.
If I'd have had time, I'd have had a T-shirt made up. I don't know what I would have put on it, but somehow that would have figured into it. I appreciate you all coming. Thanks. If you have other questions, stick around. We can talk about it. Our next talk will be Tuesday, November the 15th. A little earlier than we normally have it in the month, but the Tuesday after that, we're basically closed. Oh, I'm sorry. That's not quite true. I'm not department head, but sometimes you just can't get out of the mode. All faculty are expected to report on that day, but there will be no classes held, so there won't be any students here then. So we're having it on the 15th. Alejandro Saldivar is going to give a talk on compass-only constructions. Now, this is cool because I'll be real quick. Euclidean geometry was based on a number of things, an axiomatic structure, but also when you actually went to construct geometric objects, triangles, rectangles, and everything, you had to construct them using a compass, a straight edge, and that was it. The straight edge couldn't have a mark on it, couldn't be a ruler, and the compass had to be collapsible. I gave Alejandro my collapsible compass to use. Okay. It's a piece of string. But it was shown, I'm going to say probably 19th century, I could be wrong on that, it was shown that you don't even need the straight edge, that everything that could be constructed with the compass and straight edge can be constructed with the compass alone. And he's going to talk about that. So that's Tuesday the 15th. And my understanding is that in December, we have another talk by a student, and you're going to talk on?
It's kind of like where calculus and statistics meet, and so how we use integration to find probability.
Oh, man, yes. Wonderful stuff. Great, thanks. All right, thank you all for coming.